7.3 Second order non-homogeneous differential equations. Now, second order differential equations of the form a lots of d squared y over dx squared plus b lots of dy over dx plus cy equals f of x are non-homogeneous, and we can rewrite this equation as a times y double dash plus b times by y dash plus cy equals f of x, where y double dash is the second derivative with respect to x and y dash is the first derivative with respect to x. Now, to solve an equation of this type, you first find the general solution of the corresponding homogeneous differential equation. Now, for a homogeneous differential equation, we have a lots of d squared y over dx squared plus b lots of dy over dx plus cy equals 0. And when we solve this, we get what is called a complementary function. And once we have found the complementary function, you then need to find a particular integral, pi, which is a function that satisfies the differential equation. The form of the particular integral depends on the form of f of x. And we've got this table over here, which provides some particular integrals to try. So, if f of x is of the form p, then our particular integral is of the form lambda. If f of x is of the form p plus qx, our particular integral is of the form lambda plus mu x. If f of x is of the form p plus qx plus rx squared, our particular integral is of the form lambda plus mu x plus vx squared. Now, we still use this form over here of the particular integral for functions such as 4x squared or 1 minus x squared. We don't necessarily need a x term for this quadratic. If we have p e to the kx for the form of f of x, then the particular integral is of the form lambda e to the kx. And if f of x is of the form p times by the cosine of omega x plus q times by the sine of omega x, then the particular integral is of the form lambda times by the cosine of omega x plus mu times by the sine of omega x. And we still use this form of the particular integral for functions such as sine 2x or 5 cos x. In other words, if we've got something involving sines only or something involving cosines only, we still use this form. A particular integral is a function which satisfies the original differential equation. So let's take a look at a couple of examples to help illustrate all this. Now, for example number 11, we have to find a particular integral of the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals f of x. And we've got different scenarios for f of x. Now, what I will do is I will combine this with example number 12, where we have to find the general solution to the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals f of x, where f of x is these functions over here. Now, for us to find the general solution, if we take a look at the notes, you'd find over here, to find the general solution to the differential equation a times d squared y over dx squared plus b lots of dy over dx plus cy equals f of x, we solve the corresponding homogeneous equation a times d squared y over dx squared plus b times dy over dx plus cy equals 0 to find the complementary function. We then choose an appropriate form for the particular integral, and we can do that by using this table here, and then substitute into the original equation to find the values of any coefficients. And then the general solution, that's the sum of the complementary function and the particular integral. So we're going to be using these ideas to help us solve the differential equations as we see in example number 12. So what we see for example 12, for us to find the general solution to this differential equation, our first step is to solve the corresponding homogeneous equation. In other words, we've got the right hand side equaling 0. So if we solve d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 0, our first step will be to find the solutions to the auxiliary equation. So for the auxiliary equation, we have m squared minus 5m plus 6 equals 0. We can factorize this, and factorizing we have m minus 3 lots of m minus 2 equals 0, from which we can see m is either equal to 3 or m is equal to 2. We have two real roots. So therefore, for the homogeneous solution, YH, which is the same as the complementary function, we have ae to the 3x plus be to the 2x for arbitrary constants a and b. For part A of the question, we're solving the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 3. Now, we've already found the complementary function. We now need to find the particular integral. And if you recall from the table which we introduced earlier, what you'll notice over here, f of x is of the form p. So, for the particular integral, we will try y equals lambda. And the idea is over here, we're going to find out what the value of lambda is. So we need to differentiate twice. So we have dy over dx, which is equal to 0, and d squared y over dx squared equals 0. We now need to substitute these into here. So we have 0 minus 5 lots of 0 plus 6 lots of lambda equals 3. 6 lambda is equal to 3. Lambda is equal to 1/2. So knowing that lambda is equal to 1/2, we can therefore conclude that the particular integral is equal to 1/2. So therefore, the general solution, that's equal to the sum of the complementary function ae to the 3x plus be to the 2x plus the particular integral, which is 1/2. So this is the general solution to the differential equation. For part B of the question, we're solving the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 2x. Now, of course, we've already found our complementary function. That's over here. So now we need to find the particular integral. So for the particular integral, if we go back to the table which we introduced previously, you'll notice over here we have f of x of this linear form, and therefore our particular integral will be of this form here. So for the particular integral, we will try y equals lambda plus mu x. So now we need to differentiate this twice. So we've got dy over dx equaling mu, and d squared y over dx squared equaling 0. We now substitute these into here. So if we do that, we've got 0 minus 5 lots of mu plus 6 lots of lambda plus mu x. This is equal to 2x. So we have minus 5 mu plus 6 lambda plus 6 mu x equals 2x. And if we compare coefficients, let's just write this down. So let's compare coefficients. Comparing the numbers, you can see here we've got minus 5 mu plus 6 lambda equals 0. And if we compare the x's, you can see we've got 6 mu equals 2. So from this, you can see here, mu is equal to 1/3. And when mu is equal to 1/3, if we substitute back into this equation, you can see lambda is equal to 5/18. So therefore, knowing the value of mu, knowing the value of lambda, we can substitute back into here. So therefore our particular integral is equal to 5/18 plus 1/3 x. And therefore for our general solution, that's equal to the sum of the complementary function, which is a e to the 3x plus b e to the 2x plus the particular integral. So we add on 1/3 x plus 5/18. Part C, we've got the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 3x squared. And what you'll notice over here, f of x is a quadratic, so therefore for our particular integral we're going to have something of this form. And remember, previously we've already found out what the complementary function is. We did that at the start of the example. That was a e to the 3x plus b e to the 2x. So what we will do now is, for the particular integral, we will try something of the form y equals p plus qx plus rx squared. So, if we find out what dy over dx is, you'd find dy over dx to equal q plus 2rx, and d squared y over dx squared, that's equal to 2r. We will now substitute these into here. So what we have then is 2r for d squared y over dx squared minus 5 lots of q plus 2rx plus 6 lots of p plus qx plus rx squared. And all of this is equal to 3x squared, as we see over here. So if we expand and simplify, we've got 2r minus 5q minus 10rx plus 6p plus 6qx plus 6rx squared. This is equal to 3x squared. So now what we can do is gather all the terms involving an x squared. So if we do that, you can see we've got 6rx squared. If we gather all the terms involving an x, we've got 6q and we've got minus 10r. So we add on 6q minus 10r x, and in terms of numbers only, we've got 6p, and then we've got 2r and minus 5q. Okay. So all of this is equal to 3x squared. We can now compare coefficients. Let's just write this down. We will now compare coefficients. So if we do that, if we compare the x squareds, we have 6r on the left hand side. On the right hand side we've got 3 of them. So therefore r is equal to 1/2. If we now compare the x terms, we've got 6q minus 10r equals 0. So we know that r is equal to 1/2. So we've got 6q minus 10 times by 1/2, which is 5. This is equal to 0. Q is equal to 5/6. And if we compare the number terms, you can see here we've got 6p plus 2r minus 5q equals 0. So we've got 6p plus 2r, so that will be plus 1, minus 5q, so that will be 5 times by this, which is 25/6. All of this is equal to 0. So therefore we have over here p, which is equal to 19/36. So knowing the values of p, q and r, we can therefore conclude for our particular integral we have y, which is equal to p, which is 19/36 plus q times by x, so we add on 5/6 times by x, plus r squared, so we add on 1/2 times by x squared. So therefore for the general solution, we've got over here the complementary function a to the 3x plus be to the 2x plus 1/2 x squared plus 5/6 x plus 19/36. Part D, we've got the differential equation d squared y over dx squared minus 5 times dy over dx plus 6y equals e to the x. And what you'll notice over here, f of x is of the form pe to the kx. So for our particular integral, we're going to have something of this form over here. So what we will do is, for the particular integral, we will try something of the form y equals lambda e to the x. And if we differentiate this, you'd find dy over dx to equal lambda e to the x, and d squared y over dx squared, that's equal to lambda e to the x. So we now need to substitute these results into here. So therefore we've got lambda e to the x minus 5 lambda e to the x plus 6 lambda e to the x equals e to the x. You can see here we end up with 2 lambda e to the x equaling e to the x. So therefore lambda is equal to 1/2, and therefore for our particular integral we have 1/2 e to the power of x. Now you'll recall for our homogeneous complementary function we have a e to the 3x plus b e to the 2x. So therefore our general solution y gs, this is the sum of the complementary function a e to the 3x plus b e to the 2x plus the particular integral 1/2 e to the x. Part E of the question, we've got the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 13 times the sine of 3x. And what you'll notice over here, if we take a look at the right hand side, you can see f of x is of the form p cos of omega x plus q sine of omega x, and therefore our particular integral will be of this form over here. So for the particular integral, we will try y equals lambda times by the sine of 3x plus mu times by the cosine of 3x. And then if we differentiate this twice, we've got dy over dx, which is equal to 3 lambda cos 3x minus 3 mu sine 3x. And if we differentiate once again, d squared y over dx squared, that's equal to minus lambda times by the sine of 3x minus 9 mu times by the cosine of 3x. We will now substitute these results into what we have over here on the left hand side. So we've got minus lambda times by the sine of 3x minus 9 mu times by the cosine of 3x minus 5 lots of 3 lambda times by the cosine of 3x minus 3 mu times by the sine of 3x plus 6y. So we add on 6 lots of lambda times by the sine of 3x plus mu times by the cosine of 3x, and this is equal to 13 times by the sine of 3x. So now if we gather everything involving a sine x, well, we've got minus 9 lambda minus 15 plus 15 mu, and then we've got 6 lambda as well. So we've got here, if we compare coefficients, comparing the sine 3x terms, we've got minus 9 lambda plus 15 mu plus 6 lambda equals 13. So we've got minus 3 lambda plus 15 mu equals 13. And if we compare the cosine of 3x terms, we've got minus 9 mu minus 15 lambda plus 6 mu. This is equal to 0. So you can see here we've got minus 3 lambda, minus 3 mu minus 15 lambda equals 0. So if I call this equation 1 and this equation 2, solving them simultaneously, you can see lambda is equal to minus 1/6, mu is equal to 5/6. So with this we can conclude, for our particular integral, we've got minus 1/6 times by the sine of 3x plus 5/6 times by the cosine of 3x, and therefore for our general solution we have ae to the 3x plus be to the 2x minus 1/6 times by the sine of 3x plus 5/6 times by the cosine of 3x. You need to be careful if the standard form of the particular integral contains terms which form part of the complementary function. If this is the case, you need to modify your particular integral so that no two terms in the general solution have the same form. So for example, this situation occurs when f of x is of the form pe to the kx and k is one of the roots of the auxiliary equation. In this case, you can try a particular integral of the form lambda times x times e to the kx. So let's take a look at an example to illustrate this. Example number 13, we have to find the general solution to the differential equation d squared y over dx squared minus 5 lots of dy over dx plus 6y equals e to the 2x. So first thing we can do is find out the homogeneous equation, and we do this by setting the right hand side equal to 0. And if we do that, we've got d squared y over dx squared minus 5 lots of dy over dx plus 6y equals 0. We now form the auxiliary equation, and if we do that, we have m squared minus 5m plus 6 equals 0. So we have m minus 3 lots of m minus 2 equals 0. So therefore m is either equal to 3 or 2. We see here we've got real roots. So therefore the homogeneous equation is equal to ae to the 3x plus be to the 2x. Now for the particular integral, you'll notice over here we can't just try a particular integral of the form lambda e to the 2x. That's because you'll notice here we've got a e to the 2x term as well, and we see that in this paragraph over here. So what we'd have to do instead is modify our particular integral so that no two terms in the general solution have the same form, and we do this by multiplying by x. So we will try for our particular integral y equals lambda x e to the 2x. So now if we differentiate this, we can differentiate using the product rule. So dy over dx, that's equal to 2 lambda x e to the 2x plus lambda e to the 2x. And if we differentiate this to find the second derivative, again using the product rule, we end up with 4 lambda x e to the 2x plus 2 lambda e to the 2x plus 2 lambda e to the 2x. And if we tidy this up, you can see here we've got 4 lambda x e to the 2x plus 4 lambda e to the 2x. We will now substitute these results back into here. So what we end up with is 4 lambda x e to the 2x plus 4 lambda e to the 2x minus 5 lots of 2 lambda x e to the 2x plus lambda e to the 2x, and then we've got 6 lots of lambda x e to the 2x, and all of this is equal to e to the 2x. So we now need to tidy all of this up. So if we tidy this up, well, if we consider the x e to the 2x terms, we've got 4 lambda, and then here we've got minus 10, and then we've got plus 6, so that will be 0. And then in terms of the e to the 2x's, we've got 4 minus 5, which is minus 1 on the left hand side, and on the right hand side we've got 1. So you can see here by comparing coefficients, we've got minus lambda e to the 2x. This is equal to e to the 2x, and therefore lambda is equal to minus 1. So knowing that lambda is equal to minus 1, we can therefore conclude over here our particular integral is equal to minus x e to the 2x. And therefore the general solution, that's equal to the homogeneous equation ae to the 3x plus b e to the 2x minus x e to the 2x. So this is our final answer. When one of the roots of the auxiliary equation is 0, the complementary function will contain a constant term, and if f of x is a polynomial, you will need to multiply its particular integral by x to make sure the particular integral does not also contain a constant term, and it's similar to the previous example which we've just seen. Example number 14, we have to find the general solution to the differential equation d squared y over dx squared minus 2 lots of dy over dx equals 3. Now, what we need to do first of all is set the right hand side equal to 0, which will allow us to find out the auxiliary equation, which will allow us to find out the complementary function. So first of all, we need to consider d squared y over dx squared minus 2 lots of dy over dx equaling 0. So therefore, for the auxiliary equation, we've got m squared minus 2m equals 0. So we've got m lots of m minus 2 equals 0. So therefore, m is either equal to 0 or m is equal to 2. So therefore, you can see here, we've got real roots. So, knowing that we've got real roots, our complementary function, that's equal to a, e to the 0, which is simply 1, plus b e to the 2x. And now for the particular integral, you'll notice over here, we can't just try y equals lambda, because the homogeneous equation contains a constant term as well. And as we said over here, in that situation, we multiply the particular integral by x. So therefore, for the particular integral, we will try y equals lambda x. So therefore, dy over dx, that's equal to lambda, and d squared y over dx squared, that's equal to 0. And substituting everything we know, you can see here, we've got 0 minus 2 lambda equals 3. So therefore lambda is equal to 3 over 2, minus 3 over 2. So therefore, for the particular integral, we've got y equaling minus 3 over 2 x. And therefore, for the general solution, we've got a plus be to the 2x minus 3 over 2 times by x. This is our general solution.